Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will continue with our discussion on generating functions. I would like to introduce formal Laurent series, their relation with rational functions, and I will make some brief comments about convergence when you think about infinite series like this. Okay, let's start with a little bit of notation. So let's use the usual notation z of variable z. So these are polynomials. It's the set of all polynomials in the variable z with coefficients that are complex numbers. And there are sort of two ways I can generalize this. So I can look at all polynomials in the variable z and z inverse. So these are called Laurent polynomials. So for example, something like z plus 2z squared minus 4 c inverse is in here. Or as we've seen already, so I can generalize this to formal power series. So the symbol that is typically used is sort of a double bracket like this. So these are all formal infinite sums where the term is ak zk and the ak's are complex numbers. Polynomials are part of this set because polynomials are formal power series with only finitely many terms. Okay, and so now the common generalizations of Laurent polynomials and these formal power series are now formal Laurent series. So these are, I can think of them as formal power series in the variable z and z inverse. And so we will write a formal Laurent series. It looks just like a power series, but I'm now allowing indices that are both positive and negative. So what's in this set? Well, of course we have all the formal power series in there, all the polynomials, all the Laurent polynomials. Yeah, so this includes, for example, our geometric series that's in there. But now we also have things like, let's say, something that looks like a geometric series, but we have both positive and negative powers of z. If you've taken a course in complex analysis, then you've seen Laurent series and you've seen that they're very useful. They play the same role as Taylor expansions play in terms of expanding analytic functions. But Laurent series help if I have singularities. So for example, if you have the function e to the power 1 over z. Okay, so let's think about some properties. So in this set over here, there's a natural addition, and that's the same addition that you have on polynomials. So we add two formal Laurent series by component-wise adding coefficients. We can also multiply by scalars. And so what this means is that the set, let me abbreviate the Z and the Z inverse like this. This means that this is a vector space over C. So you can ask yourself, can we multiply within this set of formal Laurent series? And I invite you to come up with some examples that multiplication is not well defined. However, what is okay is multiplication by a Laurent polynomial. So I claim this can be defined the same way you define polynomial multiplication. If you know some abstract algebra, then you know this set of Laurent polynomials is a ring. You can add and multiply, and you stay within this ring. And what I'm saying about these formal Laurent series now is that they form a module over this ring. So to express that this multiplication by Laurent polynomials works and is well defined in the language of algebra makes this set of formal Laurent series a module over this ring of Laurent polynomials. If you don't know this language, that's fine. Just think of multiplication by Laurent polynomials to be well defined. And so now we want to get to the point of rational functions. How can we describe that? So let's say we have some formal Laurent series, maybe let me call this f. And so now what can happen is that I have two Laurent polynomials, we call these p and q, such that I happen to be in the situation that f times q is equal to p. As an example, think of f as the geometric series. And then we know, for example, because of long division, or if you can just verify that, if we multiply this geometric series by the polynomial 1 minus z, we get the polynomial 1. And so what I'm describing over here is a subset of all formal Laurent series for which a process like this works. We can find two Laurent polynomials p and q in this fashion. So this is certainly not true for all formal Laurent series, but there are some, like this geometric series. So let's define the subset. Maybe let's call it R of z. So this is a subset among all formal Laurent series. It's defined to contain those formal Laurent series that satisfy this condition. Yeah, and so what this is getting to is I have now an actual map from this subset to the ring of rational functions. Namely, if I have an element here, then I know I have some Laurent polynomials P and Q, such that F times Q is P. Then I will map this formal Laurent series to the rational function P over Q. Okay, so the first thing you should ask me, is this map well defined? And that's not clear. This needs a proof, but I claim you can prove that. The second thing we should mention, again, this assumes that you know some abstract algebra, is what I'm describing here is a module homomorphism. Both of these sets, you can realize, are modules over this ring of Laurent polynomials. And so I claim my map here is a modular homomorphism. Again, if you never played with modules, that's fine. Just think of this as a sort of a nice map between these two sets. And maybe the last thing we should talk about is sort of like what are general properties of this map. Let me give you a classic example, and that example is that of this sort of variant of the geometric series where I have both positive and negative powers. So you might ask, is there a way of writing this in the form of a rational function? And if you think about this for a moment, we can do the same trick as what we do with the geometric series. Multiply by 1 minus z. But now if you multiply this out as formal power series, there's nothing left over. And so what that means is that this sort of formal Laurent series over here in my map gets mapped to the rational function 0 over 1 minus z, and so that's 0. So what this tells you is that my map over here is not injective, correct? So I just showed you a formal Laurent series that maps to 0, but certainly the 0 function of the 0 series is a fine formal Laurent series that also gets mapped to 0. My function over here is not injective. In the language of algebra, what we have is we have a non-trivial kernel. And now we can ask, okay, what is this kernel? And I claim that kernel in some way is generated by this formal Laurent series and that we just saw maps to 0. Let me make two remarks here. One is about issues of convergence. So whenever we deal with these generating functions, there's always people who say, what about if we want to do analysis? Don't we have to worry about convergence and so on? I invite you to meditate on what we've done so far and realize we don't necessarily need the concept of convergence. But starting with this formal Laurent series that I just wrote down, I want to make at least a remark. And so what I'm going to do is I will write this now as a sum of two sort of geometric series. Of course, I maybe should rewrite this as a geometric series in the variable 1 over z. So let me now play analysis over here. My first geometric series converges to 1 over 1 minus z. The second one converges to 1 over z over 1 minus z. And so by now you should probably feel uncomfortable, and maybe I should put a question mark over here, because there's convergence issues. So what am I saying over here? So this geometric series, if I worry about convergence, has the condition that absolute c is less than 1. This geometric series, again, if I worry about convergence, has the condition that 1 over z, absolute value, is less than 1. So that's the same thing as saying absolute z is bigger than 1. What that means is if I worry about convergence, my last equation here is really not okay, actually. Those two series in the world of analysis, they live on two different planets. However, if you take this and actually do the math, what happens here, so let's actually simplify this. So I have 1 over 1 minus z, and in the second fraction, let me just multiply through by z. On top and bottom, I get a 1, and then on the denominator I get a z minus 1, and well, this is 0. So somehow, if I think about convergence, this doesn't make sense. So what I'm writing down here, right? So at the end of the day, you have that this infinite formal Laurent series, is equal to 0, which is, certainly is not. But you can tell I'm doing something wrong. Namely, I'm throwing in two convergence property that contradict each other. At the same time, my result is not exactly super wrong, because on the previous slide we saw there's a way of at least mapping this formal Laurent series to something that should be very much considered 0, namely in the world of rational functions. And so in some sense, if you want to make this rigorous, right, so what's the problem over here? The problem is this equation. And so I claim what we did on the previous slide is we replaced this equation by a map. And this makes everything actually work out just fine. So if we think of this equation as not something that is given by algebraic manipulation, or I should maybe say analytic manipulation, but if we somehow think of this as a map that's smartly constructed, then what we're doing here is actually on a sound footing. And what I'm claiming is what we did on the previous slide with this map from the subset of formal Laurent series described here to the ring of rational functions. This is what makes everything tick all right.